All right, let's dive into one of the most fundamental ideas in all of digital privacy, symmetric cryptography. It's a concept that is, both elegantly simple and incredibly powerful. And it's what keeps our secrets safe every single day.
I mean, think about it. You hit send on a message, and you just trust that it's for their eyes only. But what's actually stopping someone from taking a peek while it's in transit? How does a bunch of math actually keep a secret?
So here's the whole idea in a nutshell. You start with your message, right? The plain text. It gets locked or encrypted using a very specific key. After it travels across the internet, the person on the other end uses the exact same key to unlock it. The entire system, the whole security of it, hinges on that one single key being shared and kept secret.
And that, right there, brings us to our first big idea, this concept of a shared secret key.
The easiest way to think about it is this. There isn't a separate key for locking and another one for unlocking. No, in symmetric cryptography, it is one key for both jobs. That's it. So obviously, the entire security of that message depends completely on keeping that one key a secret between you and the recipient.
Okay, now for the really cool part. How does a computer actually lock the message with this key? Well, the answer is a surprisingly simple, almost magical, logical operation. Let's take a look at the magic of XOR. XOR, or exclusive OR, is the real workhorse here. And you can forget complex math for a second. The rule is incredibly basic. If two bits you're comparing are different, the result is a 1. If they're the same, the result is a 0. That's the whole thing.
See? It's that simple. Inputs are the same, you get a 0. Inputs are different, you get a 1. This simple act of just comparing and flipping bits, well, that's the secret weapon for this kind of encryption. So, how does this super simple logic create such powerful encryption? Well, it's basically a 3-step dance. First, your message and your secret key get turned into long strings of 1s and 0s. Second, the XOR operation is applied, 1 bit at a time, to both strings. The jumbled up result? That's your encrypted message, your ciphertext.
And here is the real magic trick. To decrypt the message, you don't have to do some complicated reverse operation. No, you just do the exact same thing all over again. You take that encrypted message and you XOR it with the very same secret key. And poof, your original message just pops right back out. It's perfectly, elegantly reversible. So, we've got the theory down, but how does this actually apply to real-world data, which isn't just a single letter, but, a continuous flow of information? Well, that is where we get to stream ciphers. Right, so your message, a video, a phone call, whatever, it's a continuous stream of bits. What the algorithm does is it takes your relatively short secret key and uses it kind of like a seed to grow a very, very long matching stream of key bits that looks totally random, but it isn't. And that's why we call it pseudo-random. And this is the core formula. Your original data stream, the plain text, is combined with this generated key stream using that XOR operation we just talked about. The output is a continuous, encrypted stream of ciphertext. It's the exact same logic we saw before, just applied on a massive, continuous scale. Now, this idea of a key stream has a theoretical, perfect version. It's sort of the holy grail of cryptography, and it's known as the one-time pad. And understanding it really helps us see the trade-offs we have to make in the real world. So what does it even mean for something to be unbreakable? Well, it means having perfect security. And that's a formal definition. It means that seeing the encrypted message gives an attacker absolutely no clue, zero information about what the original message was. They're just left with pure guesswork. And this really highlights the crucial trade-off. A one-time pad, on the one hand, uses a truly random key that's just as long as the message itself. This makes it perfectly secure, but also completely impractical. I mean, can you imagine trying to securely share a secret key that's the size of a feature-length movie? A stream cipher, on the other hand, uses a much shorter key to generate that pseudo-random stream. It's not perfect, but it's incredibly strong, and most importantly, it's practical for everyday use. So this isn't just theory, right? This practical method is running on devices you use every single day. These secrets are, quite literally, in your pocket. I mean, just think about it. The A5 algorithm, that protects calls from your phone to the cell tower. The infamous RC4 was used in older Wi-Fi, and today modern super secure messaging apps like Signal and Threema use advanced stream ciphers like Cha-Cha 20 and Salsa 20 to protect your texts. This stuff is absolutely everywhere. So we've established that this process is fantastic for confidentiality, for keeping the content of your message a secret. But there's a catch. And believe me, it is a very big one.
And here it is. This is the key takeaway, the one thing you really have to remember about stream ciphers. They offer no integrity.
Okay, so what does that actually mean? It means that an attacker might not be able to read your message, but they could, potentially, flip some of the bits in that encrypted data while it's traveling to its destination. And because of the way XOR works, this would change the final decrypted message on the other end, and you'd have no way of knowing it even happened. It protects secrecy, but not authenticity.
And that leaves us with a final, critical question. You see, confidentiality is only half the battle. If a stream cipher keeps your message secret, what other cryptographic tool do we need to make sure that it arrives exactly as you sent it? Well, that's a story for another time.